the input intrusion detection system to, let's say that if this scores it's really exceeding the threshold that has given to the input detection system, like 10 times greater, then we can say that we can flag anyway the proto alert as an alert. And then we have another information that we can use. Well, this is generally not provided by signature-based system like Snort, for example, because Snort is like reassembling the old connection payload and then looking inside for attack pattern. But if we think about an anomaly intrusion detection system that is considering a single packet to generate the alert, then we can also think that if more than one single packet has been flagged as anomalous, then we can say that if we have a large number of these anomalous packets incoming in our network, we can flag anyway the alert as a real alert, as an incident, and not just as a false positive. So to test finally our idea, to see if our idea was really working, we choose two different ways. We choose a public data set that, let's say, help us in showing to the community that what we have done is really working. And then we choose a private data set that, of course, cannot be disclosure for privacy stuff and so on, as you all know. And let's say that this was like just a proof for us, so we can publish the result, and we will show you the result, but you have to believe us. Okay, so and then we had also to test if our idea was working as we made one of our requirements to the architecture to work with both signature and anomaly-based system putting as input system. So we tested with Snort, and we coupled it also with our own system. So Poseidon was used in once was used as input as also as output anomaly detection system. So this, let's say that this way of testing the system can grant us to, to have a good architecture, that the idea is really working, that it's not just our mind. So if you're not familiar with DARPA, DARPA is a very famous and old, unfortunately, dataset that has been presented in 1999 for an intrusion detection system evaluation phase. And let's say that it has some weaknesses inside. That's why we choose also to have our data private data set. But because it cannot be considered anymore a good example of the nowadays traffic. But anyway, let's say that his weaknesses don't really affect our system because we are not taking into account those parameters that were used to tune the system that has been presented in 1999. So our private data set is a dump of 5 days of HTTP traffic. As I said before, we are mainly focused on protecting what today is a hot topic, so web application. And we collected it from our network of our university. We didn't inject any kind of attack, so we had to rely only on what the users were, or the possible attackers, or the scanners, most of the time, were doing outside. And we didn't tune the data set in any way. So I think that you know that to have a good anomaly detection phase, most of the times the training data set is cleaned. I mean, there is somebody that is inspecting and taking out everything that it's not, that it's already an attack, to have the most suitable data set to train the system. So we didn't do that. It was a choice to see how strong was our system in a real condition, because when somebody is deploying an intrusion detection system, they don't have time to clean the data set. The data will be the same that the system will see every day. So these are the benchmarks. On the left part of the picture, you can see what has been done with DARPA. And on the right side, you can see what has been done with our private data set. So unfortunately, Snort was not able to find any kind of attack in our data set. We were expecting something like this because Snort doesn't have signatures for scanners or for particularly web application like, for example, PHP MyAdmin or something like that. So even if we detect the attacks on this kind of web application, we couldn't test Snort. So there are only, here we present only the test with Poseidon. What is really interesting, for example, in the first two columns of the HTTP protocol, you can see that Snort scored a detection rate of close to 60%, but he also had almost 600 false positives. So for 600 times, the people at the IT department were going to be disturbed by this. When we apply our architecture, so when we put together Snort with Aphrodite, then we have the same detection rate, so no affection on the completeness of the system, but the accuracy of the system is really improved. We have only 5 attacks. Well, let's say that Poseidon has the same, on Poseidon we have the same effect, but because in Poseidon originally we have 100% of detection rate and only 15 false positive, okay, it's 0, but it was easy to achieve this. Let's go, for example, for, well, the SMTP protocol. Okay, Snort was okay, didn't detect any kind, didn't produce any kind of false positive. Poseidon, because it's based on, it's examining a single packet, so there were almost 6,000 half false positive, but here you see now that we have less than half, so it's close to 3,000. So again, the architecture is working, and you can see that everywhere, except with Snort on SMTP that didn't produce any kind of false positive, we have a reduction. Can be quite a huge reduction in false positive or a smaller one, but also on Telnet, for example, Snort produced almost 400 false positive, and we have only 6 now. Okay, our private data set with Poseidon, we had, without Aphrodite, we have more than 1,500 false positive, and then when putting together with the architecture, we have less than half, so we have 774. In this case, this is a very good result because we didn't clean the data set. In the other case, the DARPA data set had a training set completely clean, so we used the completed clean data set, and then in the evaluation data set, there were the attacks. So, because nowadays we have to rely on dirty, let's say dirty traffic, and we don't have the possibility to clean all this traffic to feed the anomaly detection system, the result with our private data set is quite good. What we can add this? Well, so you have seen that, well, we have seen that our architecture is working, and let's say that now there are some open problems. We have implemented Aphrodite for in that way with an anomaly detection system, not only because we wanted to, well, let's say that we wanted to reduce the workload of the IT personnel. So if I've seen system that tries to reduce false positive, making a person classifying all the traffic. So there is a person that has to classify all the alerts that have been produced by an intrusion detection system, and then the system is learning how to classify unwanted attacks. But in this case, and the system has to be retrained every time, every like week, this person has to again train the system. So in this case, we don't need to overload the personnel, the IT personnel, because we just need to set up some basic parameters like the threshold that we need to check if the output, for example, the output is exceeding this threshold, and some other few parameters. So right now, we would like to, what we are researching is a way to make this completely automatic. So to set out in an automatic way the threshold, if possible to clean as much as possible the data training set, again in an automatic way. And we have already seen that Aphrodite can work also with dirty data sets, so with dirty training data sets. So we can say that right now the system is already more than a stable, more than a developing version. It's almost quite stable. So, question time. If somebody has two questions. Oh. Yes? Well, let's say that the only problem right now is to make the input intrusion detection system able to communicate with our correlation engine. So, for example, with Snort, it was a very easy implementation because the correlation engine was looking inside the database that was used to put the alerts of Snort, and this was made in real time. So as long as there is a common platform for the two systems to talk, then it's okay. But let's say that this was like a proof of concept. Let's say we built the architecture, we verified that the architecture is working, and then we can think how to link the architecture with the input intrusion detection system. But yeah, the problem is to make them talk. Other questions? Yes? Okay, the question was how we can inspect our traffic, how can we characterize the traffic? Well, you mean how we know that outbound traffic is related with the previous connection, or what we look exactly inside? Okay, we inspect the payload, only the payload. So we look at the header field of the packet to link it with to track the related connection. So the connection that has been opened by this client to this server. And when we have tracked the connection, we inspect only the payload. So the problem is right now that the response of the server can be quite huge. For example, if we think of a normal web page can be around 30 kilobytes. So we have to inspect quite a huge packet, and that was the problem of using the original pale system or using other anomaly detection systems that are on the market right now, because so they are quite good in detecting something in the input, because commonly the input is quite small, but when you have to look on for the response, then the response is quite huge. So if we are on a Ethernet network, it's around almost 2 kilobytes. And when we will have IPv6, maybe, finally, then it will be greater. And that's the problem. But the system, let's say, responds quite well to this problem. Okay? Did I answer you? Okay.